Perimeter Institute under the advice of G. Vidal, the legendary co-founder of the MRG algorithm, and who is now based in Google. After completing his PhD, Yijian moved to Q Farm at Stanford. He spent 3 years as a postdoc fellow there, and now he moves back in Canada, and is currently is currently a postdoc fellow back in KITP, and having spent much time doing conformal field theory, today he's at Fields Institute talking about some of the CFT work and mixed plane phases is doing. Let's welcome you.
So yeah, thanks Yijian for the introduction and thanks for the invitation. It's my great pleasure to be here. And so let's just get in. Oh, sorry. Okay. So today my talk will be about critical mixed state spaces. So as seen from the title, first is a critical state, meaning that it's long range correlated with power law correlation functions, and secondly is a mixed state, which is not as usual like a pure state in your sense of quantum phase transitions. So I will tell you like a long story that dates back to 2 years ago, starting from this paper and a companion paper, also with Chen Ke and so on, and then the other papers I will briefly talk about are like some of the recent work with Saga Vijay's group and also with Yongbak and Yijian here, which is about like a more recent experimental verification of the result and also some new progress. So let's get started. So when we talk about phase of matter, so there's some setup that we have to first fix, which is local Hamiltonian. So we usually consider a lattice, usually a regular lattice, and then we consider some local Hamiltonian that is geometric local on this lattice, and then you diagonalize this Hamiltonian and you get the ground state and low energy excited states. You basically find 2 scenarios. One scenario is that, one scenario is called gapped, where you have several low energy eigenstates that is very close, which typically exponentially close in system size. And then you have a finite gap that doesn't decay with the system size. So you get some finite gap to some excited state, and then you also could have other states. And this is indicated by the gap space of matter, where at low energies or at low temperatures, your physics is dominated by this degenerate subspace. And this could happen, for example, for multi-insulator, where it's a trivial insulator, where you only have one ground state, or you could have topological order, or symmetry protected topological order, or spontaneous symmetry broken states. Like all of these are in the category of gapped phases. But today, I will more focus on the second, more complicated and more interesting case, which is gapless cases, where as you scale the system up, like you make the system size larger and larger, you find that your low energy spectrum will become very, very dense. Like in fact, there are infinitely many of low energy spectrum that will come close to the ground state when you scale the system size. So the gap will just scale to 0 as n goes to infinity. And that includes examples where, for example, metals, where you have a Fermi surface. And then perhaps today's talk more focused on quantum critical points, which is described by conformal field theory. Okay, so now I want to tell you about some indications of quantum phase of matter based on quantum entanglement. So recently, not so recently, but like a great theme of this century is to see some interconnection between quantum information and condensed matter theory. So let's say, well, what's actually the quantum information property of each of the phase of matter that we just talked about? So in this talk, I will just give you these 2 examples just for a taste, but yeah, but there are certainly very, very more on entanglement characterization of quantum phases. So the logo or the motto is that states of non-trivial phases are characterized by long-range entanglement. So by long-range entanglement, so there will be a precise definition here, but yeah, but let's say the long-range entanglement can be indicated by some of the entropy functions. For example, for the 1D critical quantum spin chain that is described by conformal field theory, what you get is you take a ground state and you take a subsystem with some length A, and then you compute the entropy, and the entanglement entropy will scale as logarithmic of A, and with a proportional constant that is called central charge. And this is very different from the SSB, I mean simultaneous symmetry breaking or gapped phase in one dimensions, where if you take the entanglement, it's just saturated to a constant. Like in this case, if you consider, in the critical case, if you consider A to be large enough, then the entropy will be divergent. So that's a distinct characterization that distinguish critical system with gap system. So that's the story in one dimension. And in two dimensions, space of matter are much more intricate. And for example, you can have something called topological order. And in that case, you will find the entropy of a subregion satisfies the area law, which has a proportional to the length part. But then there's also a constant piece, which is universal and actually carries the information of the anion data and the topological quantum memory. So so this constant term also indicates like universal properties of phases. Okay, so now so all of this, like this gamma and this C, they are indications of long-range entanglement. A precise formulation of long-range entanglement is to say that two pure states are in the same phase if and only if they can be connected with local unitary transformations. By local unitary transformations, you can think of it as a brick wall or a finite time evolution of a local Hamiltonian. So by this formal definition, two states are in the same phase if they share the same long-range entanglement properties. That is because like local unitary transformations can only screw up degree of freedom locally. It cannot really change what happens at longer scales. So that is the formal definition. And a non-trivial state basically saying that you cannot use the local unit transformation to transform back to a trivial state, like a product state. And all of this, like the critical system and topological order, they are examples of non-trivial phase. Okay, and today I'm going to talk about going beyond the usual pure state paradigm and mixed state, talk about mixed states. So, okay, mixed state is very natural in quantum information theory, but why do we care about it nowadays in condensed matter? That is because first, it is experimentally relevant, and then secondly, there are actually interesting phases that go beyond pure states. So the experimental relevance can come as like noisy quantum simulations or open quantum system, or thermal, like a simple thermal state, or in quantum error correction code where you subject to some errors and then try to correct, then you are basically encounter some mixed state. So now the question is, can we extend the previous definition of like long-range entanglement like to mixed states? Actually, there are a lot of recent progress on mixed state phases, such as topological order and SPT. Like they come up like there's a lot of papers in these 2 years or 3 years. It's a very hot topic, and yeah, I think like the understanding of topological order and SPT, they are still not very complete, but yeah, there are still many recent progress. If you are interested, you should follow that. Today, I'm going to talk about not gapped case, a generalization of the gapped case, but the generalization of the gapless case. So I will going to talk about mixed state critical phases. Okay, any questions about the introduction? Okay, good. Okay, so I will first give you an example where a critical mixed state can appear with non-trivial properties. So let's start with the pure state. Okay, well, I will talk about a model that everyone knows, that is the critical Ising model. And this model is characterized by a single parameter G, which is the transverse field. And when the transverse field is 0, you get actually a double degenerate symmetry breaking state, which is the GAZ state. And then when G goes to infinity, you get one ground state, which is the product state. So there must be a phase transition going around here because you are changing your ground state degeneracy from 2 to 1, and it exactly happens at G equal to 1, which is determined by Coulomb-Mannier duality. And this point is described by conformal field theory. And in order to distinguish this conformal field theory point with other points, you can actually compute the 2-point correlation functions. You find that they are not exponential decaying; they are actually polynomial decaying, and the polynomial here is characterized by this exponent, which is known as the scaling dimension. And in fact, if you compute different correlation functions, you will actually get different exponents. That's actually very important here. So you get 1/4, 9/4, and 2 for the x, y, z correlations, and these two will correspond to different fields in the conformal field theory. If you are familiar with that, and this number will actually be very important later on. Okay, so that's the Ising model, and then what we want to ask. Sorry. Then what we want to ask is that now what happens if I put this system on a quantum computer and then I let the environment to decohere the system? So we need to model the decoherence as a quantum channel. So now you start with the ground state psi, and then you do a quantum channel N that sends this psi in general to a mixed state. And in this case, for theoretical understanding, I'm not taking correlative noise. I mean, in principle, the analysis will also work for short-range correlative noise. But let's actually take an independent noise model where at each site you subject to dephasing channels, the same dephasing channels. That is, of course, determined experimentally by your device. Okay. So the dephasing channel is in the cross representation looks like this, where you define a vector v in R3 and actually on the sphere, and then you compute the Pauli matrices, and then you use the Pauli matrix to conjugate the density matrix, and that represents an error. And there's a probability p to have an error, and probability p 1 minus p to don't have an error. So then after that, this is the dephasing channel you get. You can alternatively rephrase the noise as the environment tries to measure the system at the probability p. Okay. So the question is whether the dephasing channel will get you, into a non-trivial phase of matter, and here by non-trivial phase of matter we actually means long-range entanglement properties. And as a reminder that for critical mixed state, what you have is the characteristic logarithmic scaling of entanglement. So now for the mixed state, we would like to say okay, whether the logarithmic still survives, whether the coefficient change, this kind of, and we are going to answer this type of questions. And the spoiler is that all of these will be very strongly depending on the direction of the dephasing, like depending on which the direction you choose to dephase for the Ising model. Okay. So the main result is that entanglement quantities can actually change abruptly as you tune decoherence. So one example is that the coefficients of the log could just suddenly change to 0 when you tune a little bit of decoherence. And the reason for that is that now these quantities, they are actually not a usual kind of observable in your like in the state. It's not an unusual observable which is linear, like trace of rho times some operator. The entanglement properties, they are not linear, and for example, this Renyi entropy, all this negativity, like generalization of negativity with a Renyi index. So these two, if you look at it, they have a power n, so they are not linear. So actually, they can change very much as you tune, as you just make a little bit decoherence everywhere. So that's distinct from like local observables. Okay, so we discover a new mixed state phase of matter that's connected by some sort of RG flow. One example is that now we can have dephasing in the x direction, in the z direction, in the y direction, and in the zx direction, meaning somewhere in the zx plane. Okay, so now you have this 4 mixed state, and we discover some kind of RG flow, or also identity channel, meaning the original pure state. You have these five mixed states, and which we find that they are connected by some sort of RG flow. And this RG flow is dominated by, changing of the logarithmic coefficient of the negativity. For example, the x dephasing here, if you turn on a very small x dephasing from the identity channel, so you will be here. And then because of the RG flow, it will actually be equivalent at long scales to the complete x dephasing. So this actually means that even a very weak x dephasing will destroy almost all long-range entanglement, because under the RG flow, it will flow to strong x dephasing. And on the other side, you will find a irrelevant perturbation, which is like the y direction dephasing. It actually preserves almost all long-range entanglement. And that is because you are irrelevant. So if you turn on a small y dephasing, you will flow back to the identity channel that is no dephasing. And z dephasing is a little bit weird. It can be irrelevant or marginal. I will be more detailed later.
So that is connected. What are you connecting here? The argument is that again there is a map or an operator. Previously you said for pure state, you can have unitary evolution.
Yeah.
Operator connected. So is that an argument here as well?
Yes. Yes, the connection is information. Yeah, okay. There will be a more precise version, but the statement is that suppose you can use some channel like to okay, sorry. Actually, it's not. So okay, I will just say it. Okay, so the equivalence relation of pure state phase coming from local unitary transformation, and the equivalence of relation of mixed state come from local channel transformation. And in this case, because we are dealing with critical point, we don't actually need. We will just lose the requirement of locality like a little bit. Okay, and then the statement is that with this dephasing, you are going to a different phase, so it's not possible to go back, use a local channel back to the pure state. Yeah, but for this y dephasing, you can actually go back, and this actually is very much related to quantum error correction. Like, yeah, so this, you regard this as a noise, and then you use a quantum error correction, and you find this noise is correctable, this noise is not. Yeah.
Is there an intuitive reason that when I add the noise, I should expect that this doesn't break your conformal symmetry?
Okay, I will actually show you that it will map to a conformal defect problem.
Okay. And one more question is, so for these examples, we always lose entanglement.
Mm-hmm.
Is there an RG flow for anything that would increase my entanglement? Like I have some notion of a C theorem thing, like can I say?
Yeah, there is a notion of C theorem. Yeah, it's not in the negativity, but it's in some other quantity. Actually, it's in this quantity that you can prove some kind of monotonicity theorem. Okay. Yeah, but in this example, actually, it's coincide. Like this also like it's only destroying. Oh, the Renyi index. Yeah. Oh, what is Renyi index? You're asking what is the Renyi index?
In this context, there's significance.
Yeah, sure. Yeah, the RG flow will also depend on the Renyi index. It will be important. And okay, so actually the most important Renyi index is 1, which is corresponding to the von Neumann entropy or Shannon entropy, right? So yeah, that is one example, but we will also try to focus on like n equal to 2 and n equal to 3 case, where it's easier to deal with. So
any index being n in your equation.
Yeah. Okay.
So classically, this would correspond to different moments of statistical distribution.
Yeah. So yeah, what I think it's actually very important for this Renyi index to be greater than 1 for this to be held. It actually, if you take n equal to 1, it's actually become a different phase diagram. So yeah, and the intuitive understanding is that n greater to 1 is only sensitive to larger eigenvalues of rho, and n equal to 1 is actually like sensitive to all the eigenvalues, and n smaller than 1 only sensitive to small eigenvalues of rho. So that's kind of an intuitive argument, and in fact, like this kind of phase diagram also strongly depends on whether n is greater than 1 or smaller than 1. So it's actually a very important number here. Okay. Oh, sorry. I guess there's some problem with this PowerPoint presentation. Actually, yeah, somehow it becomes like this. Sorry for that. Oh, this is supposed to be okay. Just let me say in words. Okay. So now I want to I want to tell you a little bit more about what's the difference between entropy and negativity, because they actually measure different kinds of correlations. So if you just okay, so remember that now we are in a mixed state, right? Our mixed state is bipartite into A and A bar. So A and A bar, they are system, and the environment. Of course, there are some environments that make a purification, right? That is like, yeah, that is how the noise is implemented. And then, of course, A is correlated with A bar, but A is also correlated with the environment. A bar is also correlated with the environment. So what we want to do is we want to actually first separate the environment out. We don't want to consider the environment. We only want to consider correlations within the system, like between A and A bar. So one way is to consider the entropy, but if you consider entropy of A, it actually measures the correlation between A and A bar, but also A with the environment. So that's not a good quantity we consider. Instead, we consider the mutual information. So here is supposed to be the mutual information. It measures the correlation. So this mutual information meaning that you have the SA plus SA bar minus SAA bar. And this measures actually both classical and quantum correlations between A and A bar. Sorry, so this should be A and A bar. Okay, so the way to see that is that even you have a classical state, meaning that the classical mixture between A and A bar, you still could have some non-trivial mutual information. So mutual information actually captures classical correlations also. But for quantum correlations, you are actually instead not using the mutual information in this black box, but you use the negativity. So the negativity is defined in this way, where you need to take the strange replica limit to get to the so-called logarithmic negativity, and it has shown that for a separable state, for a separable state, meaning meaning that you can prepare A and A bar just with classical resources. These quantities they are actually zero. So both of this linear version and this logarithmic version they are equal to zero. So actually these quantities, both this and this, will be some kind of indications of quantum correlations. So here, we will actually be more interested in quantum correlations rather than classical correlations. So this will be an important quantity. Okay, so let me show you the result in more detail about what's the RG flow, what's the monotonicity theorem. So now remember that our dephasing has a characterization in terms of a vector in the S3, but now let's restrict it to the ZX plane. So there's a single angle theta that characterizes this direction, and you do the dephasing with some strength, with some strength p, and then what you will find is that the logarithm, the entanglement entropy, actually here the Renyi entropy, just goes like a volume law minus some constant. The volume law is actually very easy to understand. That is because you are applying dephasing everywhere, so your system are locally entangled with the environment. And remember that this quantity also captures the entanglement between the system and the environment. So there is a volume law term. But then what's non-trivial here is that you also get a constant term. So let's look at this constant term and see what happens. So here I'm rescaling theta from 0 to pi over 2 to 0 to 1. That's just a simple rescaling. And then you compute this log g and you compute different system size. And then what you get is kind of an indication that there are only three fixed points. Where first, if theta equal to 0, you get 0, and then if theta is between 0 and 1, what you get at long distance is that it will go to this value, go to this smaller value. And if you choose theta prime theta equal to pi over 2, that is in the x plane, in the x-axis, then what you get will be this point. So you basically see there are three kind of renormalization fixed point, and by renormalization fixed point, I mean properties doesn't change with system size, right? So you basically see that this is a kind of an RG fixed point, and something in the middle is like an RG fixed point, and theta goes to 1 is a RG fixed point, right? And you also see a RG flow structure that the flow is going from the 0 and 1 to the middle. And in order to make this flow actually clear, you can actually do a so-called scaling collapse. Let's see here, like this diagram is basically like a redrawing of the diagram of this part. But now instead of drawing different lines that correspond to different system size, I'm rescaling the parameters with system size to some power. And then you magically find that all this, like all these lines will collapse into one line. That is clear indication of critical phenomena, right? Like it's very common in critical phenomena where you increase your size, you have some effective strengths, effective perturbation strengths will just increase because of a relevant perturbation, and you will use a positive coefficient, positive exponent here, which is the critical exponent, to collapse a single line, which means that under the RG flow, your effective noise parameter scales in this way. Okay, so here so there are some critical exponents. So it indicates that when you turn the noise from here to here, from z to x, you will encounter three kind of fixed point, which is like for z you get 0. For x, you get minus log 2. For zx, you get minus 2 log 2. So this is a numerical number, but actually there's some way to actually explain that. But the key observation here is that you observe something like the monotonicity statement, right? Here you can only, like when you increase the system size, you find that your log g can only decrease. Like here it is very clear that when you increase the system size, log g just decrease. Here is also, right? So so this is some kind of indication of monotonicity, and it's actually related to the defect problem, so which will be shown in a slide later.
0.5, is this something you fit, or from your theory you know the
fit.
critical exponent? Oh, it's okay.
Yeah, So yeah, the beginning of this work is all numerics, and I believe that the complete explanation of field theory is still missing.
Okay.
Yeah.
Big state actually.
Oh yeah, it's this state. This state. Yeah, so you have the ground state under this decoherence. Yeah. In this calculation, I use p equal to 1, but but because of this relevant perturbation, p equal to actually 0.1 gives you the same result. Okay. So that's the change. That's this boundary entropy and sorry, log g. Okay, I spoil it as something called boundary entropy, but yeah, the physical interpretation is something called boundary entropy, as you will see later. Okay, and then as I promised, we need to look at an activity, and an activity is supposed to have a logarithmic scaling in a pure state. Like here, look at the blue line, which is this line. Okay, so it's going to be a logarithmic scaling, okay, so now a little bit different is that now instead of using log of LA, you use this factor, which comes from a conformal transformation to a cylinder, if you know conformal field theory. So it's basically equivalent to log LA, but for a periodic system. And then what we want to know is what is this coefficient? And in fact, now you will find three kind of behavior. one behavior is that for X dephasing, with a very small noise strength, okay, 0.1, you see the negativity will become this. Oh, it's like a constant. So there's nothing like a growth, logarithmic growth anymore. So it's a constant. And for Y dephasing, I guess it's this line. I think the colors somehow changes because I transmitted file to the new laptop. But yeah, but this is the Y dephasing. So you basically see, oh, they are parallel, right? So they are parallel, meaning that they only differ by this order one term, which is non-universal, like which we don't care. It's the same for the coefficient. For the coefficient, they are the same, meaning that you are kind of encounter irrelevant perturbation. That is, this universal piece is the same, meaning that you stay in the same phase, roughly speaking, right? And for Z dephasing, you actually observe something like a continuous change. Like here, you have this orange line, which is has the strength 0.p equal to 0.2, which is like this. And you have 0.4, which is like this. You see all of them, they are logarithmic with non-zero coefficient, but this coefficient is continuously decreasing towards 0. Of course, if you take like p equal to 1, you will get complete dephasing. Then you get a classical state. There will be no activity at all. So at p equal to 1, you will basically collapse the Z dephasing also to a flat line. But at finite p, what's interesting is that you still have this logarithmic scaling, but the coefficient is continuously changing, and that is signaling a marginal deformation. And if you look at this figure, you find you see that this log G, which is supposed to be monotonic on the RG flow, doesn't really change under the Z dephasing. So here I use a dotted line, which means a marginal deformation. So this figure and this figure actually agree with each other in the case that it says that Z dephasing is a marginal perturbation, and all the universal properties will change continuously. And if anything is monotonic, then it won't change. Okay. And now I'm mapping the problem to a field theory problem, which will be very brief, but I hope it will illustrate the point. So basically, we write this Renyi entropy, which is like this n rho is like the mixed state we are considering, and to the power of n, you consider this generalization of purity nth moment to a path integral. And if you consider a path integral of this, then what you basically get is a path integral on 2n copies of CFT with some boundary condition. So yeah, the math is actually straightforward. Like if you work out a little bit, you will immediately recognize that it will be a boundary condition. And here, if you want to consider negativity, then you want to consider this type of quantity. Then basically what you get is again some kind of boundary condition, but there will be two different boundary conditions on A and A bar because you are doing a partial transpose on A. So the boundary condition will be different. So there will be some kind of boundary condition changing operator you inserted here and here. That will basically give you this logarithmic form. And of course, if the logarithmic form has 0 coefficient, that means the boundary condition changing operator has scaling dimension identity, which means that essentially the two boundary conditions are the same. So that's what happens for the X dephasing. But for the Z dephasing and the Y dephasing, you actually see a non-trivial delta. So that means that these scaling dimensions inserted between these boundary junctions, they are non-trivial. And what about the G function? The G function is just simply you put your boundary conditions everywhere here. So yeah, so it's actually here. Yeah, actually here. So the G function is like you put a boundary condition like here. So it's a closed loop. So we know that the correlation function of a closed loop in a conformal field theory, of a defect loop in a conformal field theory, is given by this Affleck-Ludwig entropy, and it's shown in this paper, Friedan and Konishi, that this boundary entropy is monotonic on the RG flow. So yeah, so all of this seem to agree with the field theory prediction that this subleading constant in the entropy must be monotonic on the RG flow, and also the logarithmic coefficient agree with the boundary condition changing operators here. So then we need to know whether the perturbation is relevant or irrelevant. In order to say that, we actually have to see what kind of boundary condition we put here. So effectively, okay, I'm skipping the proof, but effectively, by turning on a small channel, small defacing channel to the state, you are effectively creating different perturbations on this boundary. So for the x defacing, you introduce x times x. For y defacing, you introduce y times y. For z defacing, you introduce z times I. And then they have different scaling dimensions as I showed in the first slide, right? X has scaling dimension 1/8, so x times x has scaling dimension 1/4, which is smaller than 1 and making the relevant perturbation. So it will be a relevant perturbation, meaning that, okay, the defacing will be stronger and stronger at longer scales. That's agreeing with our expectation. And then for the y defacing, you actually get this 9/4, which is greater than 1. So you get a relevant perturbation. And for z defacing, you get exactly marginal because delta equal to 1. And that means that your perturbation changes continuously, like this defect universality class changing continuously. So the scaling dimension of this boundary changing operators also change continuously.
Why is C defacing Z times I?
Yeah, that is actually simply because they have a non-zero expectation value. Yeah. So, but x and y doesn't.
Okay.
Yeah. Okay. So what about other Rayleigh index? So I said that like Rayleigh index is very important here, but actually it turns out that it's not, that does not so affect the phase diagram instead of like this replica limit, which is the von Neumann limit. So all n greater or equal to 2 became similarly, x defacing is always relevant. It will make the negativity at order 1 at any finite strength. Y defacing is always irrelevant. But yeah, the non-trivial thing is that for the z defacing, it becomes irrelevant instead of marginal when you take the replica limit. This is actually shown in our more recent paper on in quantum error correction, in the context of quantum error correction. Okay, so I think that's the first part. Yeah, any questions here? Okay, so
For specific for this model Hamiltonian, now with the Ising model,
yeah,
once you change the model, you pick the Ising model to be that interaction along the like classical one. You would switch the direction of the which direction of the decoherence is actually playing a role. Okay, so it's tied to your
yeah. So the fact that x is relevant, of course, depending on the choice that you have xx minus z. Yeah, but the point is that all of these, they are universal. Even if you change the convention of the Ising model, you add interactions, there will be still some kind of boundary condition that corresponds to it.
Depends on the type of CFT as you showed in the other work.
Yeah.
Can use the same CFT correlation for
What did you do the numerics with?
You mean with
Like waiting for these, you're defeating.
for this?
Yeah.
Oh, you mean how did I do that?
Yeah.
Metric product state.
Okay.
Yeah, so that's the magic here, which allows us to do 100 something type size.
Finite system.
Yeah, finite periodic system that's conformally equivalent to infinite system. That's the truth.
Right. Okay. So have you thought about like if you did like IDMRG or something, would you give you the fixed point, like if you went to a truly infinite?
Oh, because IDMRG is not faithful either, right? Like, IDMRG has a finite bound dimension,
right,
which effectively cuts you to a finite system. And the boundary condition is actually very non-trivial because like this boundary condition is not determined by the finite correlation length. Right. And yeah, we don't want that to corrupt our data.
Okay, I see.
Yeah. So periodic is cleaner. Yeah.
So one more question, if you go to models with beyond nearest neighbors couplings, how much of this space have you checked? Because you had in the Ising model, was it nearest neighbors?
Yeah, nearest neighbors. Yeah. I guess I didn't check it, but the effect should be the same. Like you observe basically the same behavior because the field theoretical explanation is basically you turn on some perturbation that corresponds to sigma, and it's relevant. If corresponds to actually here, the descendant of sigma is irrelevant. So this is correspond to the epsilon operator is marginal. So this part only depends on, universal data. So yeah, and also if you change to the strip state port model, you will also find a similar behaviors. Yeah. Oh, use measure product density operators, right? Like now instead of one leg, you have two legs on each side. Yeah.
And did you use a language like a package or?
Oh, I wrote it by myself.
Okay.
Yeah. So I guess that's only my choice. But if you want to do it, you actually should use the package. But I don't know which package can actually help you to do this because this is a non-trivial calculation. Yeah.
Imply tensors.
Okay. Yeah. You could use tensors for DMRG to get the ground state, and then you do some tensor operations on front of that. Yeah. Okay. Okay, so now we have all these theoretical and numerical observations, and now can we actually see this in an experiment? So that's a work mostly by Yijian. So the trick to measure all these quantities like nonlinear observables, like trace of rho to some power, is given by this paper, a famous paper by Huang. Okay, I misspelled it. Huang, Keng, and Priskill.
Don't give this talk at Caltech yet.
Sorry about that. And yeah, the technique is called shadow tomography. Yeah, so basically you start with some product state, you prepare the critical ground state using variational circuit, which is also what Yijian is good at. And then you add some noise channel just by doing random bit flip. And then you do shadow tomography, and shadow tomography meaning that now you apply a random unitary at each site, and then you do a z-basis measurement. And after that, you put these unitaries and the measurement result into a classical computer and try to do a post-processing classical algorithm to reconstruct the whole state or some activity or all the Renyi entropies and so on. Yeah, so the logo of this process is called measure first, compute later, because like you measure this, you get some random, you get some shadows, meaning like shadows in some random directions, and from this shadow you can actually construct many properties. So you don't actually have to first determine what kind of properties you want to measure. You actually only reconstruct the properties you want in the last part. So you can do your experiment and store your data in some cloud, and everyone can share those data, and then everyone can actually compute the same the same quantity as you want, or they can try a different quantity using the same data. Okay, so this is a very efficient way to actually measure all the quantities we are interested in. And for example, for the Renyi activity, remember we have this theoretical prediction, which is on 64 sites using MPS, and then you have this experimental result on 6 sites. So for very small system size, but still you see some signatures here. Like for the no dephasing, of course, this is this one, but for the X dephasing and Z dephasing, you clearly see that the dephasing is still increasing. But the X dephasing is very small, like the activity becomes very small. Although it's not really clear that it's, in this case it will be error law because of the experimental error, but yeah. But still, you see that X will decrease your activity a lot, meaning that it's relevant. And Z dephasing still shows like logarithmic scaling with a smaller coefficient, indicate it's marginal. So that's the indication. And then there's another more interesting quantity, which I didn't show in the previous theoretical part, but it's actually in our new work that we show that this quantity could also indicate mixed state phase transitions. So this quantity is called Renyi correlators. So instead of consider the usual correlation functions like trace rho O, you actually consider a Renyi version of that, and you choose O to be O1 times O2, then this is the definition of Renyi correlator. And here I'm choosing this O to be XX, like I compute the XX correlation, and you will basically see the same indication as like what we see later, that is X dephasing is going to be a relevant perturbation, and Z dephasing is going to be like a marginal perturbation. And the way to see that is, okay, first from the MPS simulation, you can also compute that. So you see that for the X dephasing, what you get at long distance is a constant. That means that's roughly like symmetry breaking, simultaneous symmetry breaking, right? Like in simultaneous symmetry breaking, you compute the correlator for n equal to 1, and you find that the connected correlation function, if that is all the one that indicate a spontaneous symmetry breaking, that means you are in a gapped phase, right? And here, in accordance with the X dephasing being a relevant perturbation, you observe that the Rayleigh correlator is saturated to a constant that also indicate, some kind of long range order. So that is also agree with the fact that an activity being area law, right? So then for the no dephasing, of course, get some power law decay, but for the Z dephasing, you get a faster power law decay. So that and also this slope of this fast power law decay depending on the strength continuously, depending on the strength of the dephasing. So this is the marginal perturbation. So experimentally, what we can see is that X dephasing clearly makes your Green correlator larger, and it makes the decay slower. And for the Z dephasing, it makes the Rayleigh correlator smaller and also the decay faster. Yes. So that's the experimental signature using the Rayleigh correlators. And if you take a closer look at the Rayleigh correlator, there are actually something new that you didn't expect. That is, for example, you look at this quantity, the Rayleigh XS correlator in the previous slide, and then you minus the final value. But you take the because here you see a tail, like a very small tail, right? And you just try to extract the constant value and try to see what's the tail behavior. And the tail behavior is actually a power law. So you see when for the X dephasing, all of this data for X dephasing. For X dephasing, it's a relevant perturbation. So all of the p's are the same because all of this they will flow to p equal to 1. So they belong to the same universality class. So the fact that they are parallel is not surprising. But what is surprising is this exponent, this 1 minus 1.25. We don't know how to explain that. And for the Z dephasing, for the X dephasing, and if you consider ZZ correlator, but the connected version, like this one, basically you also subtract the infinite, the infinite value, then you will basically observe the same thing. That is the slope of all these, they are the same, and the slope is some mysterious number, minus 3.5. Yeah, so ideally this should be explained in terms of some defect operators in the icing model, because the whole problem is mapping to a defect. But yeah, currently because of the field theory, people they don't know how to do with this kind of defect. So the precise explanation of these numbers is currently unknown. So yeah, it will be great if we could actually work out analytically all the defect operators and see what this how these numbers come from. Okay, so that's the some more recent part on on the same model. And then how much time do you have?
Like 5 more minutes.
Okay, 5 more minutes. Okay.
The experiment was done on a simulator. The
It,
experiment is still a simulator. Where you just stay in the sim. Yeah,
It's a quantum. It's a quantum. It's a quantum. You should mention it's a quantum H1 cation. So it's a real experiment.
Also, it was on a machine.
It's on the quantum. Yeah. It's on quantum.
yeah, sorry.
Okay.
Yeah, I guess. Did I mention that? Okay,
Yeah.
but
Just because the title was on a quantum simulator.
yeah, it's a quantum simulator. Yeah.
Yeah, I mean, it's a quantum
Oh, if I understood.
quantum
Yeah, understood.
simulator of
Yeah,
the
okay.
physical
Yes, yes.
Yeah.
Okay.
quantum processor.
Yeah.
Yeah.
Simulator.
Oh, okay. Okay, sure. Yeah, quantum processing. Okay, and then I will go to another model, which is the Lotny liquid, which like the ground state of Lotny liquid, and I will use another trick to prepare the mixed state. But now the mixed state is not generated by local decoherence, but by measurement and feedback. So okay, since I don't have too much time, I will go through the conceptual framework on it and skip out all the details. So so the projective measurement and feedback comes in the mathematical way like this. If you write this as a channel, so it means that you measure in a complete basis that is projective measurement with this projector PM, and then you first measure them, and then depending on the measurement outcome, you apply a different unitary depending on the measurement outcome. So the unitary is conditioned on outcome. So that makes a generic quantum channel. You can actually verify this is a cross representation. And then the good thing about this is that it can actually induce non-unitary evolutions because you have measurement, and could generate long-range correlations because there's no Lieb-Robinson bound, because you can transfer your classical data, like you can collect your classical data from very far away and determine this use. Even though these use they are local, but the subindex M can be non-local, right? Because you can measure very distant qubits. So in general, this is kind of a non-local transformation. So just give you one example how this could be useful. For example, you can use measurement feedback to prepare a GAZ state even in constant depth. Usually in unitaries, you cannot. Like you can only do it in linear depth. So the way is to start from the product state and you measure all the domain wall operators. And after you measure the domain wall operators, you try to apply the sigma x simply to eliminate all the domain wall. And now you eliminate all the domain wall regardless of like your measurement outcome, then you are guaranteed to get a no domain wall state that is either 0, -1 or the GAZ state or the other GAZ state, which is 0, -1. And the reason why this get a plus sign is that you have a strong symmetry. You have a strong symmetry that is like a product of X that is kept in all the process. So you start with a symmetric state. In the end, you must get a symmetric state. So that's how you ensure that you get a GAZ state from this measurement process. And in fact, you can also consider like producing a toric code state. That's also the most important, most easy way to implement the toric code ground state, because you can measure all the stabilizers and then try to eliminate all the anyons. That's basically the same story. Okay, so now you see that it can introduce long-range correlations even in this single step. And in this case, I will try to look at what happens for the critical states. Okay, so the critical state we are having in mind is the Large liquid, which is described by the spin-fold fermion. And of course, here no interaction is added, so it's corresponding to a particular large parameter. And what we do is we measure the charge on each side. So the measure the total charge. The total charge could be 0, 1, 2, because now it's a spin-fold fermion. And you make a feedback on the spin sector, which means that now you collect all the information from the left of a side. You collect all the number of all the measurement outcomes, some of them, and then you make a unitary only on one side, that depending on this measurement outcome all to the left, and this unitary is simply on the spin sector. Only on the spin sector, and there's a delta parameter that is the feedback strength. So as I said, like here it's a quantum channel that is going to be of this form. And now what you can ask, what's the mixed state you are getting? And the mixed state actually still has a power law, like because the reason is that you can just do an analytical computation that this like for example the spin correlation functions will be a string operator. Like under this measurement feedback, basically you map your local operators to a string operator. So the expectation value on the mixed state of local operators will be the original expectation value of a string operator. And luckily, this string operator also has a power law decaying, thanks to this paper. This is called some kind of hidden parameter, hidden order parameter in large liquid. Okay, so now you have mixed state that is still power law correlation. Then the question is, what's the entanglement properties? Do we create a new mixed state phases like beyond pure states? Okay, and sorry for this slide. This is just the technical way to deal with it. We actually deal with them basically analytically because of its free boson. So basically what we do here is that we first write down the large liquid and then we try to bosonize all the operators, like the number operators, the spin operators, and the measurement of the charge essentially becomes measurement of the charge field phi, and the feedback simply becomes feedback on the spin sector boson field. So yeah, all of these, they are continuous description of the discrete protocol that I just described. And then once you have this protocol, you can just do an analytical calculation of all the density matrix, and you find this horrible phenomenon, horrible string, but this horrible string is quadratic. It's quadratic in the field. So that's important. That allows you to do some analytical calculation, and this is the result. The result is actually enabled by using some tricks by Youngbach 10 years ago. And then what you do is you can actually compute the subleading term in the entropy and also the negativity scaling. The negativity shows logarithmic scaling, but the logarithmic coefficient change continuously with the feedback parameter. So now basically you are creating a new kind of mixed state phases with non-zero gamma and also with a different negativity scaling that is not present in pure state, because in pure state the central charge cannot change continuously. But here the central charge just drops continuously with the feedback parameter. Okay, so that's the last work I just want to mention. Okay, so that's the summary. We probe critical mixed state by entanglement, and then basically we are focusing on these two quantities, one and of course three quantities. One is the entropy and one is the negativity, and then the other is Renyi correlator. And we can probe these quantities on a shadow tomography, and we basically show for the case of critical IC model on the decoherence or any CFD on the decoherence, we have RG flow that where the entropy of the subleading term of the entropy serves as some monotonicity theorem. And then for the larger liquid on the measurement feedback, we can actually map it to a free boson theory. So then some kind of analytic calculation can be done. Yeah, and okay. So last slide, what I didn't talk about, and also equally interesting, is this. So I just talked about critical mixed states. So there are general definitions of general critical states given in this paper. And then for topological phases and SPT, you should look at this paper. And also I mentioned some relation to error correction. So you should look at this paper and so on. So there are still more and more going on. Okay, so that's the end.
Students from the audience?
That when you mentioned different Renyi index for the entropy and negativity, that they sort of probe different energies, right? Can you say something similar about the Renyi correlators?
Yes, yes.
And can you see it somewhere in the results, for example, here? This change of order.
Yes, yes. Good. So let me first say that when Renyi index goes to smaller than 1, actually things become very different. For example, X defacing will become irrelevant, will become marginal. I don't understand why, but when you look at the G function and so on, you will get marginal behavior. But and then if you look at the Renyi correlator, what you get is that for the XX correlator, but with smaller than 1 Renyi index, you actually get a power law decay with continuously changing coefficients. And for the Z, you actually suddenly become relevant where you observe a straight line. That is when the Renyi index smaller than 1. So yeah, so indeed Renyi index greater than 1 and smaller than 1 seem to be very, very different. And I guess the reason is basically that this replica trick fails to generalize to like all of this replica trick fails to generalize to n smaller than 1, because n smaller than 1 doesn't make sense for replicas. Yeah, but we don't understand why for n smaller than 1 that happens. Yeah.
The monotonicity fails for smaller than 1.
Well, it doesn't. Monotonicity is still there.
In Renyi index,
You mean in Renyi index?
like it's no guarantee that it should work for smaller.
Oh, yeah. I guess yeah. There's no argument for that.
I think for integer Renyi index beyond 2, it approves like that.
Yeah.
Yeah, but below that, there's no guarantee at all.
Yeah, because the field theory just fails. Yeah. Or you encounter non-unitary field theory.
Just in the quantum information perspective, like it's not monotonicity.
Sure.
For in Renyi index.
Yeah. From an information theoretical perspective, you only monotonicity holds at the equal to y, right? Like because like strong stability and no like the negativity are monotonic only for the von Neumann version, not the Riemann version either. So yeah, it's a non-trivial thing to work out. Mhm.
Okay, any other questions? If not, let's thank Yijian again. So he will be here for the rest of the day, so if you want to talk